And now we're going to actually turn it over to Chris Johnson, who is an engineer by trade, and he's going to talk to us about learning music theory through Deltaphone. Take it away, Chris.
All right, I'm going to hit share here, share computer sound, and share. Okay.
That looks great.
Whew. Okay. Hi, everybody. I'm Chris. I'm in Wisconsin. I'm Chris Johnson from Wisconsin, if that helps. I'm a computer science educator at a university here. So I teach the folks that are a little bit older than some of you are dealing with. But CS education has had a pretty good run lately. We've got endorsements from presidents and famous athletes and musicians and household names in technology. A number of states allow computer science to count towards science, math, or even foreign language requirements. There's a couple states that even require all high schools to, in the US, to provide computer science courses. There's lots of nonprofits out there trying to increase access to computer science education to underrepresented groups. There's lots of funding. And so we should sit back and think, why is there so much attention given to computer science education? And so Paulo Blickstein at Stanford, now Columbia, did a report for Google where he identified four reasons that computer science education is getting so much attention. One rationale for it is the labor market, that we've got a tech-based economy, and in order to stay competitive, we need laborers that have computer science skills. Another rationale was the equity of participation rationale, where the most advantageous jobs and offices are going to go to people with computational skills. So in order to make sure there's diversity at all levels, we need to make sure we have computer science skills at all levels. There's the computational thinking rationale, which is the idea that computer science exposes us to problem-solving strategies that we can transfer. We can take those ideas and apply them to other disciplines. And then there's this slightly similarly named one called computational literacy, which is the idea that computer science engages learners as they build representations of knowledge, as they build up models. So each of these ideas has merits. As an educator who's in a classroom, I care less about the first three, not that they're not good, but I want immediate results. I want to think about what happens in my classroom. So these are about jobs and status and transfer. They're secondary. The thing I care most about is the learning in my students, and that's where this last one comes in. Computational literacy. This isn't just about breeding a brand new generation of software developers, but it's viewing computer science as a medium for learning in all disciplines. Just like we look at regular literacy, we consider the written word to be the way we hold knowledge and transfer knowledge. Computational literacy says that we build up knowledge by writing programs and sharing them and reading them from other people. So there's a particular kind of learning that I think computational literacy benefits, and that's the learning of music theory. So I feel a little bit in reverse of what many of you are doing, where you're trying to bring learning from other disciplines through music. I'm trying to bring the learning of music through computer science. And so this might be off your radar in some ways, but the programming is what most people think of when they think of computer science. That's the primary activity that we do. It's really time consuming, and there's a lot of heartache when you first start programming, and that's largely because we use very generic languages that are meant to serve lots of crowds. What we need are small languages that are tailored to the discipline at hand. So I've got one that I've been working on I want to share with you today. It's called Deltaphone, and we'll see some of its ideas here. I'm going to share like four qualities of programming that I think contribute to the learning of music theory. So the first one is the general idea of sequence. So if this works correctly, we should be able to write some programs here. So this is Deltaphone. It's free software. It runs in a web browser. It's available online now with all its bugs. But let's look at sequence, this idea of sequence. So I'm going to go up here and pull down a little block here. If you've used Scratch, if kids in your school have used Scratch before, this is a very similar interface. It's called a blocks programming language. So here I'm going to play a note, a C, natural in the 4th octave, and it'll be a quarter note. And in music, we often do sequences. We do scales. So let's do a quick little scale. And now for this next note, instead of thinking about it as an absolute position on the staff, the reason it's called Deltaphone is because you're thinking more about the intervals, the musical theory aspects of it. So here I'm going to go number of half steps up, or if you're in the UK, semitones, or however you call them. So we've got a C, and then we go up one step to a C sharp. Then I'm just going to copy and paste a few of these. And you can see the music getting engraved or rendered on the other side as we go. And let's just make it a full 2 measures. Okay, so here's a nice little program. And if I can move my little bar here, I should be able to play this now. All right. Was that audible, Tiffany?
Yep, it sounded great.
Okay. Okay. So we have this notion of sequence where as you write a program, you think about, hey, well, music's got this flow through time, and if you were around in the 1980s, you might have heard of this programming language called Logo, where you learn geometry by driving a turtle around the floor with a marker inside of it or on the screen. And the idea of turtle geometry was, instead of thinking about an absolute coordinate system, you thought of it in a relative coordinate system. They called it turtle geometry. So Deltaphone is really about turtle music, where instead of thinking about B flats and C's and D's, you think about what are the intervals between notes. So we can change this chromatic scale here up to a major scale. Let's just copy and paste. No, we won't copy and paste. Let's go up 2 steps and 2 steps again. We'll follow the pattern of the major scale, which goes up 2, 2, and then we go 1, and then we go 2, 2, 1, and let's see, 2, and 1. So there we go. So now we have a major scale. This should sound reasonable. There we go. If we want to change to a minor scale, it turns out we can talk about the relativity of scales. I can actually just take these last 2 blocks and drop them in here, and now I have a minor scale. If you're really big on music theory, you'll know that these are spelled wrong. These should be flats of the next note above rather than sharps, but that'll get fixed someday. So that's the idea of sequence. Let's go to the next one here. Music has a lot of repetition, some of it explicit with musical structures, with explicit repetition structures, repeats and codas and so on. But there's also a lot of implicit repetition and made up, or I'm sorry, Deltaphone supports both forms of repetition. So let's look at an example here. Let's go up by fifths, perfect fifths from a note. And let's just have a sort of a ladder of jumping fifths. So let's start here at C. Let's go down to the 3rd octave, really low. And then for our play, let's jump a perfect fifth. So there's various ways to play notes. You can play absolute notes. You can play in half step or key step, diatonic or chromatic motion. Or you can use the interval notation here. So let's go up a perfect fifth from here. But let's keep on going. And in the previous demo, I was duplicating the block, but we don't normally do that when we write programs because it's unnecessary. I'm going to bring a little loop here that happens to be called ditto. Means do the same thing again. And there I'm doing this thing twice. Let's go up, I don't know, 4 times? 5 times. Oh, that's 45 times, but it still works. But we see the results live. We can see what it means to be a perfect fifth. We can play this here. And we get a feel for that sound quality of that interval. So this is the informal repetition structure. There's also the explicit repetition structure. There's a repeat block, repeat with endings. Let's grab the repeat block and just snap around here. So now I see automatically the music gets a repeat, and let's do a little bit more to make that an actual valid piece of music. Okay, there we go. there's a bug here that the speed on the second playthrough is slower. Sorry. Okay, so that's the idea of repetition that is exposed by programming. Let's also look at another big idea of programming that helps learn other ideas of music, and that's data abstraction. So here I have a little program. It just plays quarter notes starting at C, going up. If I decide later, after I've written this, that I want these to be half notes or whole notes, I'd have to make 4 separate changes. So there's a quarter, there's a half note, there's a half note, there's a half note, there's a half note. But in computer science and in algebra, we'd like to think not in terms of these absolute values, but instead of think of things in terms of variables. And so I can use variables when I write code. I'm going to take this duration and factor it out to a placeholder. I'll drop that in here, and we will call this placeholder duration. I'll drag my half note up into here, and then I just trade places. Every place where I had a half note before, I will now replace it with the symbol. Let's drag all these out here. And now I have a half note. If I decide later that I need to change to a quarter note, I can get by with changing just one spot. Or I can change to a whole note. So this idea of symbolic manipulation is exposed through programming, and it's not just a programming concept, it's a concept we see in other disciplines too, because now I see that there's some connection between the parts of the music, that there's coherence between these what would otherwise look like separate notions. All right, the next big idea that I think helps with music is procedural abstraction. So let's look at an example here. I have a play. There's actually 4 different ways to play. There's the half-step jump, there's the interval jump, there's the absolute position, and if I scroll down, there's a very generic one that lets me do some other things here too. So this one I can attach a chord to. So right now I'm playing a C major chord, and it's defined as, you know, the root C plus 2 steps up from that previous note, plus 2 more steps up from that previous note. So this is a triad. What I can do, because there's lots of different ways to play triads, I can turn this into a function or a procedure with this block right here. It's called to. It describes a hypothetical action. And let's name it triad. And now I can issue this I can repeat this procedure many times with just by invoking its name. And so on and so forth. If I play it now, so that's C major over and over again. It turns out that what if I decide I want a slightly different chord that has a different root? Well, when you have a procedure, when you have this named operation, you can also leave little holes in it called parameters. So I'm going to add a value parameter, and we'll call it the root. So here, instead of passing in or hard coding this C note, I'm going to throw this out for a moment. And instead, we're going to start that chord at the root, whatever that happens to be. Whatever that happens to be must get determined by whoever calls this procedure. So it's got a little empty puzzle piece there for it right now. So I need to give it that root note. If I go, and while we're here, let's go ahead and make some other helper functions. Well, I'm going to make another function here called the 1 chord. So this is the 1 chord in the major scale, which will start at that scale's root. And let's just have it play a triad. And we will start it off at the note C. And then let's get rid of these here. And now if I want a 1 chord, I can do that. Now if I'd like to have say a 4 chord, let's copy this. Like so. And let's jump up from wherever we're at in the current scale here. So I think 3. Now, so I have a procedure that now will reuse that triad routine, and I should be able to get a 4 chord, like so. And there it is, starting on the F. Let's make a 5 chord. Sorry if you don't know music theory. This has all been a labor of me trying to learn music theory, and I feel like the best way for me to learn it was by coding it. And let's do a 6 chord. So now I should be able to have a little chord progression, and it's all made possible in a very compact way because I've abstracted away these procedures. So let's jump to functions and grab a 5 chord, and let's grab a 6 chord. And then why not play it many times? So let's grab a loop. And let's see how that sounds. And then if I really wanted to get into things, I could invert the chords. There's all sorts of things we can do musically to this. So, and I think in order to have a little bit of time, I'll just show a quick little demo here. There's ways in this language to also build little interactive quizzes for yourself. This is a little program that is for ear training. So it just played an interval at random. It's not showing you currently what that was. I should look at the chat to see what interval was that, people. I'm gonna click on chat.
So we have some people, we have a comment from Greg, and he says that there's a lot of actually big chords, a lot of pop and rock songs that use the 1-4-5. Yes,
there's an excellent YouTube video of, I forget what band it was that merged all these together, but yeah, that's where I stole it from. So, but so I can't remember what it was, but that might have been a second, and then it shows you the second.
So I have to say, I think you're like the definition of the interdisciplinary. So in the beginning of your presentation, you said, I might take the reverse approach to what you guys normally do, but I actually think it's really cool. So instead of actually us who are scientists that want to just use music, you're like building the music with the science, which is, it's pretty incredible.
I feel like in computer science, I'm in a supporting role that computer should be at the middle of all the other things we're doing. It itself isn't a discipline that, I mean, I teach it, and so this is sort of apocryphal that I'm saying these things, but I feel like it's glue that can help everything else, and it's helped me become more aware of what's going on in the sciences and in the arts, and so it just seems like a natural step.
Oh yeah, and so one of the questions that we have is basically, do you get people, like, people don't need any musical experience, right? Like they can sort of walk into this particular, you know, engineering class and really it sort of introduces them into the idea of music. They don't need to be a professional piano player or have any prior experience. They can actually learn it through this concept, correct?
Yeah, I don't see this as a compositional tool necessarily. I don't want to take the creativity away. It's really meant, I really do want to frame it as a way to learn musical theory. My goal is that I would find a music educator somewhere that wants to build a curriculum to teach music theory in this interactive way of, what the idea would be, you'd start with very few Deltaphone primitives, and you would build up a library of all the musical structures that we use, that we employ. And just, you'd feel like you owned the music, you reinvented it.
Yeah.
And I feel like that's kind of what I'm at here with Deltaphone. It was me trying to reinvent music, supposing I didn't have the history of, you know, that we do have. What if I had to reinvent it? This is what it might look like. But
so Greg says it's an interesting idea where computer science is like the glue rather than as a discipline of its own. So probably an interesting perspective, but yeah. And so I'll shout out there to anybody that's interested. You mentioned to me over the phone, you said that you'd love to work with a musician, right?
Yeah, I mean, yes, a music educator in particular, but yeah. Yep.
Yeah, so I think one of the things that as Voices develops a bigger collaboration, one goal that we have is to actually make a space where we can create that collaboration so that somebody like you can actually get hooked up with a music educator and you can work together. So hopefully that is in the works. But yeah, anything else that you'd like to add?
No, it's been really fun to learn. I'm really jealous. I feel like I don't feel like a singer, and I feel like there's an element of just the humanness in there that I'm jealous of. So it's been really great to see folks work. I don't know. We've got energy.
Where can people go to get more information about Deltaphone?
So let's jump out of here. The tool itself is available. Let's see if I can zoom in a little bit here for you. Deltaphone.2d is my website, and it's got my email address and so on it, but it's up and online, and you can go and build things. But deltaphone.2d.org.
Awesome. I'll just type that in the chat there. Deltaphone.2d.org. There you go. All right. Well, thank you so much. You're actually one of our first engineers, so we are lucky to have you. We appreciate you coming to our conference.
Thanks, Tiffany. Yeah.
All right.